Hello everyone, my name is Zhida Chen. I am a researcher who graduated from Nanyang Technological University. It's my pleasure to present our paper in 6 Spatial today. The title of our paper is START, a cache-based distributed warehouse system for spatial data streams. This is the outline of my presentation. Spatial data is very common in our world. Smartphones together with social network apps are producing huge amounts of spatial data every day. An example of spatial data is a geotag tweet. A geotag may be the coordinate of the user or a short text that describes his location. Geotag tweets have both spatial and textual attributes, which contain useful information for certain users. Other applications of spatial data include location-based services, such as Google Maps and Yap, both of which have many users. The widespread of spatial data makes it important to conduct analysis on it. The increasing rate of spatial data is fast. Every minute, there will be more than thousands of new spatial data get created, which can be considered as a data stream. By analyzing a spatial data stream, one can obtain much useful information. A warehouse system is a kind of system that focuses on optimizing aggregate queries. Compared with object-finding queries, aggregate queries can return aggregate information of data, allowing users to have a high-level idea of the data. It's usually more helpful for generating insights of the data, which facilitates decision-making procedure. For example, a sales manager wants to know the popularity of iPhone in her neighborhood. She can issue a query that returns the number of tweets mentioning iPhone every day within her neighborhood, and the query result can help her adjust her advertising strategy. This example shows the necessity of a warehouse system for analyzing spatial data streams. Though there exists much research work on querying spatial data, the work on developing a warehouse system for spatial data streams is still lacking. Existing works either focus on object-finding queries, lacking support for aggregate queries, or only consider stated spatial data, which have high updating latency. Some works exist for string warehouse systems like Muppet, but they do not provide native support for spatial data, making them not efficient enough for spatial data analytics. Here are the contributions of our work. In our work, we developed a distributed warehouse system named START, which optimizes aggregate query processing over string spatial data. We propose an effective and efficient workload partitioning strategy. We also design cache-based mechanisms to optimize processing aggregate queries, which includes query-based caching and object-based caching. In the following slides, I will explain them in more detail. START supports aggregate queries with ad hoc constraints. START mainly supports two representative aggregate queries. They are counting queries and top-K queries. Both snapshot and continuous queries are supported. Here are two examples showing the snapshot and continuous queries. We use keyword sync to define a continuous query and to indicate how often its result is refreshed. Before explaining the technical part of our paper, I first introduce what a view is. View is a derived relation defined by a query. It contains the result of that query. It means that by maintaining a view for a query, we can either output the view as the query result directly or compute the result based on the view with very few computations. In this example, the view is already the result of the query. The view materialization problem is to select a set of views to be materialized. In our work, we keep materialized views in memory. Workload partitioning is a very important problem to be considered when designing a distributed system. In our system, the load of a worker is composed of 3 parts. The first part is object processing cost. The second part is query processing cost, which includes the cost of snapshot query processing and the cost of continuous query processing. The last part is view maintenance cost. In a string scenario, views must be kept up to date with respect to new objects so that they can be used. The workload partitioning problem has the objective of minimizing the total system load, which is the sum of all workloads. There are 2 constraints for the partitioning problem: load balance constraint and memory constraint. The main idea of our workload partitioning algorithm is to build a quotient. The reason why we choose quotient over other spatial indexes is that it's effective in workload partitioning and it's efficient in updating when workload partitioning changes, both of which are very important in a distributed system. There are two phases in our partitioning algorithm. In phase 1, we start with one root node and recursively partition the node with the maximum estimated load. According to previously mentioned load computation equations, we need to compute querying cost and wheel maintenance cost. Since we cannot decide which wheels to be materialized in phase 1, we use the amounts of objects and queries to estimate the load. In phase 2, we use a depth-first manner to assign leaf nodes to workers. The depth-first manner is to ensure data locality. For the purpose of load balance, we estimate the average load each worker should have and use it to guide the assignment of leaf nodes. If the load balance constraint can be satisfied, we output the quotient as partitioning result. Otherwise, we go back to phase 1 to further partition heavily loaded nodes. Next, I will explain our catch-based mechanism, which include query and object-based catching. In query-based catching, we propose to use wheels to reduce the running time of queries. Low wheel materialization is a classic problem in data warehouse community. It still has several new problems to be solved for spatial data. In this example, we have a quotient, and for query Q1, we can only use the wheels maintained in nodes corresponding to cells 1 and 2 to compute the result. For other nodes that are not covered, we must check the objects in them to compute the query result. As shown in this example, we need to consider which wheels to be materialized in different nodes of the quotient. Another problem is the wheel maintenance cost. Compared with traditional data warehouse focusing on static data, we must consider the wheel maintenance cost in a string setting. In a string setting, wheel maintenance cost may be very large and outweigh its benefits of answering a query. Therefore, there exists domination relations among different wheels. We say a wheel VA is dominated by another wheel VB if the queries that can be answered using VA can also be answered using VB. And also the load of having VB is smaller than the load of having both VA and VB. In our wheel materialization algorithm, we first need to generate candidate wheels and then materialize wheels. To generate candidate wheels, we insert log queries into a quotient and find the largest node that is covered by query range. This is because that only wheels in nodes that are covered by query range is helpful for answering queries. We then add those wheels into candidates. After deciding the candidate wheels, we call a greedy algorithm to materialize wheels. With wheels maintained, we can use them to help answer queries. When a query arrives, we use its query range to access the quotient. For a node that is fully covered, we compare the cost of using its wheels and using its children's wheels. We recursively compare the cost of wheels in different nodes and decide the wheels to be used for answering queries. For nodes that are partially overlapped by query range, we must access the objects in them to compute the query result. If the amount of objects is large, the cost can be large. So to further reduce the query cost, we propose another catching technique named object-based catching. The main idea of object-based catching is to catch a subset of objects in a node and to use them to answer queries instead of using all the objects in that node. The features of catching region helps us decide which subset of objects to be cached. Based on the way how a node is overlapped by query range, we have two types of catching regions. In this example, we have side catching regions in red nodes and have corner catching regions in blue nodes. The object catching problem is to decide a catching region for each border or corner of the nodes of the quotient. The objective is to reduce the querying cost as much as possible, which is measured by the number of objects that can be avoided checking with respect to the queries. The constraint is available memory space. We propose a load-based greedy algorithm to solve the object catching problem. For each catching region, we can compute its load improvement. The load improvement is measured by the total number of objects that can be avoided checking for our queries. We sort catching regions in descending order of low improvement divided by its size. In that order, we select the catching region until there is no enough memory space. In a string scenario, we need to maintain catching regions too, so we adopt an LRU eviction policy to remove all catching regions. We evaluate start on a cluster of EC2 instances. We use Twitter dataset for evaluation. As we do not have real-life queries, we synthesize queries for evaluation. This table shows the possible query parameters for synthesized queries. These figures compare star with two other systems, Simba and GeoSpark, with respect to query response time of snapshot queries. Neither Simba nor GeoSpark works on string data. To make the comparison feasible, we create a stated spatial data set by preloading them with a stated set of tweets. The results show that star is about 3 times faster than Simba and GeoSpark. The reason is that Simba and GeoSpark are not optimized for aggregate queries with constraints. For continuous aggregate queries, we compare star with Tornado on throughput. Tornado is a distributed system for querying string spatial data. We extend Tornado to support aggregate queries. The results show that star has larger throughputs than Tornado for both Cont and top K queries. To conclude, we propose a distributed string warehouse system named star for spatial data analysis. Star is optimized for aggregate query processing. We design effective workload partitioning strategy considering minimizing total system load and load balance. We present catch-based mechanisms to reduce the running time of aggregate queries. Experimental results demonstrate the good performance of our system. That's all for my presentation. Thank you for your listening. Thank you.